So buffers. If you add an acid or a base to most solutions, the pH is going to change a lot. The presence of a buffer helps to mitigate that. It resists pH change. And so a buffer is going to contain significant amounts of a weak acid and its conjugate base, or it could be a weak base and its conjugate acid. If you just have a weak acid or a weak base, it doesn't have enough of the conjugate to act as a buffer. So let's look at this. This is an acetic acid acetate buffer. So acetic acid is the weak acid. We're going to pour that in here. And then we're also going to pour in here a solution containing acetate ion, which is the conjugate base of acetic acid. So we're using sodium acetate, could be potassium acetate. That sodium is just a counter ion. So we add that in here. And now we have sort of equal amounts of acetic acid and acetate ion. And we've got some hydronium ions, and there's sodium ions floating around too. But now if I add acid, the acetate ion can neutralize that. If I add a base, the acetic acid can neutralize it, because we have plenty of both. Any questions yet? So can we identify a buffer? Which solution is a buffer? What are we looking for? A weak acid and its conjugate base. So these all have acids here. Are they all weak acids? No. Letter B, HNO3 is a strong acid. I did not want to do that. I wanted to do this. So that one's out. The others are weak acids. And now we need to find the one that has the conjugate base for HNO2. So the conjugate base will just have the hydrogen ion taken off. So you might be looking for NO2 minus, and you're not going to see it. But what do we see that's very similar? NaNO2. Because this is, NO2 minus is an anion, and you can't just have an anion. You have to have something else with it to make it a neutral compound. So the correct answer then is D. Any questions? So how do we calculate the pH of a buffer solution? So we're going to stick with that acetic acid acetate buffer. And we have a solution that's initially 0.1 molar in acetic acid and in 0.1 molar sodium acetate. So the presence of the acetate ion here is going to affect this equilibrium. So if there was no acetate to start with, we would have this equilibrium. It would form some acetate, and we could calculate that using the equilibrium constant, the Ka. But because we're adding acetate now, it's going to affect the equilibrium. This ion that we're adding in the acetate is common to the the acid ionization equation. It's one of the things. So we're adding one of these species, and that's going to affect equilibrium. The ions are in common, and so that's called the common ion effect. So if I have this equilibrium and I add a common ion, if I add this, it's going to affect the equilibrium, right? Le Chatelier's principle. So calculate the pH of a buffer solution. It's 0.2 molar in HC2H3O2 and 0.1 molar in NaC2H3O2. Ka 1.8 times 10 to the minus 5. So we have a weak acid. Let's write the equation for the weak acid, ionizing. And then make an ice table. Okay, I don't think I like this. It's wiggling. See how crooked that eye is? That wasn't me. So what are the initial concentrations? They're given in the problem, right? So I wrote HA for generic acid. That's referring to this guy, right? So 0.2 molar. And C2H3O2 is our A minus. And so we're told that that's 0.1 molar. What's the hydrogen ion concentration to start with? About 0, yep. So this didn't come from the ionization of that. We put this in separately. So these guys were both added. We didn't add any hydrogen ion. All that's in there is what the water had, 10 to the minus 7. And so then we look at, well, how's this going to shift? How's it going to change? Well, there's a 0 on the product side. And so then this is 0.200 minus x, and 0.100 plus x. And then write the equilibrium constant expression. This is all the same as we did in chapter 16 and 17. Not 16, and 17. So products, H plus times A minus divided by HA. And then we took these guys and plugged them in for the concentrations. And we took the value of Ka and plugged that one in. And then we solve for x, right? We could try x is small, but we're not going to, because I think the solver is more fun. So it says that x equals 0.0000359 And my rule of thumb is if there's more than 3 zeros, it's probably a good idea to write it in scientific notation. 3.598 times 10 to the minus 5. And then what does x represent? It's the change, but it's also the hydrogen ion concentration, right? So this equals our hydrogen ion concentration. So then we can find the pH, take the negative log of that number. Concentration, we kept 2 sig figs, so in our pH we keep 2 decimal places. and we say that the pH is 4.44. Any questions about that? What's different here is that instead of just having the acid and watching it ionize and figuring out what the pH is, we also start out with a significant amount of the A-. And that's really the only thing that's different. So you can find the pH of a buffer solution by doing an equilibrium problem using an ice table. But there's another way as well. There's an equation called the Henderson-Hasselbalch equation. That's a mouthful, isn't it? So we can derive an equation, that equation, which relates the pH of a buffer solution to the initial concentrations of the buffer components. I'm not going to test you on this derivation. Come on. Okay. So this is very much like what we just did, except we don't actually have the concentrations. So HA, that's the initial concentration, and A-, that's the initial concentration. And the initial concentration of hydrogen is 0. And so plus X minus X, we get HA initial minus X. We get A- initial plus X. And then this is just this is just X, which equals the hydrogen ion at equilibrium. And if we want to find the pH, that's what we need, right? We need to find the hydrogen ion concentration. So we can put this into a formula. It's going to be this times this divided by that. So H plus at equilibrium times A- initial plus X divided by HA initial minus X. Great, how does that help? Well, we're not done yet. We want to know the hydrogen ion concentration. Yeah, we do. And that's the negative log, right? So let's take the negative log of both sides. So over here, I'm going to have the negative log of Ka. And over here, I'm going to have the negative log of H plus at equilibrium. And then so there's a property of logarithms that if you take the log of x times y, that's equal to the log of x plus the log of y. Don't ask me why. So here I can think of this as H plus times A minus over HA. Oh, so the other thing we need to do here, this equation only works when x is small. So if x is small, then this x disappears and this x disappears. This was also an x, that one's not going to disappear. We want an equation that's going to give us the pH. So we want to put this thing on the other side. So pH is going to be equal to pKa. I just flipped it. And then we have to subtract this. It's got a negative, so that becomes a positive. And that's the Henderson-Hasselbalch equation. What's nice about this is if you know the pKa, which you're always going to at least have the Ka, and you can find the pKa very quickly, and you know the initial concentrations, then you can calculate the pH just using this equation. You don't have to do an ice table. If you like ice tables, you can always do an ice table. That is always going to work. So pH equals pKa plus the log of, and what that was, it was the conjugate base over the weak acid. So it's the base over the acid. This will work as long as the X is small approximation is valid. So then we want initial concentrations that are not too small, and we want K to be fairly small. So if the acid and base concentration are greater than 100 to 1,000 times of Ka, it's going to work out real well. Most of the time it works. The equilibrium approach using an ice table always works. So let's try that out on this one. Calculate the pH of a buffer solution. It's 0.25 molar HCN, 0.17 molar KCN. We're given the Ka for the acid. It says use both the equilibrium approach and the Henderson-Hasselbalch approach. Which one do you want to do first? Henderson one? Okay, let's do Henderson first. So we'll write the equation. pH equals pKa plus the log of the base over the acid. Well, they gave us the pKa, right? 9.31 plus the log of. Now we've got HCN and we've got KCN. And I know some people are still a little iffy on this and look at that and you're like, I don't know what's going on here. Okay, this is an ionic compound. It's a metal and an anion. And so when you put that in water, it's going to separate into the ions. This is a weak acid, right? When it loses a hydrogen, it reveals its conjugate base. This contains the conjugate base of that. Everybody okay with that? So for the base, I use the concentration of KCN. 0.17. And for the acid, the concentration of the acid. Any questions about using the equation? So that was the Henderson-Hasselbalch approach. Now we're going to do the equilibrium approach. The equilibrium approach requires an equilibrium equation and an ice table. So here we have our acid in equilibrium with hydrogen and the conjugate base. We're going to make an ice table. I'm going to put in the initial concentrations, so 0.250, and Cn minus is 0.170, and the hydrogen is approximately 0. I'm doing this kind of fast because you should know what we're doing with this part. Plus x minus x. If you're not sure about any of it, please ask me a question. So then we write the expression for the equilibrium constant. A lot of this is kind of repetitious, isn't it? Oops. And then we put the numbers in. So they gave us Ka, 4.9 times 10 to the minus 10. That would equal x and 0.70 plus x divided by 0.250 minus x. So in the previous slide, it said that if these concentrations were like 100 to 1,000 times bigger than this, are they? This would be 2.5 times 10 to the minus 1, and this is 4.9 times 10 to the minus 10. It's 9 orders of magnitude. Yeah, x is small is going to work here. So x is small, that becomes 0. This becomes 0, which makes the math a lot easier. So I've got 0.250 times 4.9 times 10 to the minus 10 over 0.170. .206 times 10 to the minus 10. So that is our x. Anytime you do x is small, you have to check. To check the x is small, we're going to take this. Where did that come from? Let's get rid of that. We're going to take this number and divide it by one of these. We're going to use the smallest one and then multiply by 100. Is that going to be anywhere close to 5%? No. I'll just do it for fun. Is 4 times 10 to the minus 7%. Yeah, that's small. So here's our x, which is our H plus. And let's go up to the top here. So the pH is going to be the negative log of that. Which is 9.1423. Or 9.14. What do you know? Yes?
So the Henderson equation only works when x is small again.
Correct.
So how do we check x is small without solving for x?
That's a great question. So it only works, the equation only works when x is small. How do we check without finding x? That's where it was saying if the concentration here is more than 100 to 1,000 times bigger than this, you're going to be okay. Yeah. Any questions? 9.14. So a buffer has a weak acid HA and its conjugate base A minus. The weak acid has a pKa of 4.82 and the buffer has a pH of 4.25. Which statement is true of the relative concentrations? This pH is smaller than that. The pKa is the pH you'll get if these are equal. So how can we make 4.82 get smaller? Are we going to add acid or base? We'd need more acid, right? So that tells us that the acid concentration must be bigger than the base concentration. Does that make sense? The pKa gives you the pH when the concentrations are equal. That's because if these are equal to each other, this is 1 and the log of 1 is 0. pH equals pKa. So we could look at these and figure out, well, if this fraction is greater than 1, does that make a negative log or positive or what? Or, which is what I did yesterday, it was kind of a mess. Or we can just think of, okay, well, it starts at this and it has to go this way. They're only asking me which do I have more of? Well, if it's lower, I must have more acid. Okay? So buffers resist change, but the pH still will change a little bit. So we need to be able to calculate the changes in the pH when something's added to the solution. So there's going to be two parts here. The first part is a stoichiometry calculation. We're going to look at what's being added and how that changes the relative amounts of acid and base. The second part is the equilibrium calculation, which could be an ice table or it could be the Henderson-Hasselbalch equation. Okay, so the stoichiometry part is the new thing we're adding right now. So here's an example. 1 liter of a buffer, it's 0.1 molar in HA, also 0.1 molar in A minus. And it says calculate the pH after adding 0.025 moles of strong acid. So we had a buffer, and now we put something in it. So we're not going to make an ice table. This is not an ice table, and this is not exactly how your book shows it. I think the way the book does it, it's correct, but I find it a little confusing. So it took me a while, but I came up with this one. This is moles initial change and moles after. M-I-C-M-A. MICMA? MICMA. Yeah, so, I mean, whatever. What we're doing here is we're looking at, well, what did we add to the buffer? We added a strong acid. And what part of the buffer is going to react with that? The base. And that's going to form HA. So to write the equation at the top here, you look at what are you adding? I'm adding acid. Which of these is going to react with that? Well, it's going to be this one. So write the equation for those reacting. We're going to assume that they react completely, hence the single arrow. We're going to put in what is initially there. So this is what we're adding, the 0.025 moles. And notice this is moles, not concentration. And here, A minus, 0.1 moles. It's 0.1 moles per liter. Just I can't explain it, but I see it a lot. Chem 1B students forget what M means, the capital M. I guess it's kind of understandable. There's so many M's. So this is molarity, moles per liter. It's not mole. Mole is mole. Right? But if you don't have that straight in your head, you can make a lot of mistakes and get a lot of questions wrong. So this amount of moles happens to be the same as the concentration because I have 1 liter. The moles of HA, also its concentration times the volume. Okay, so now we have a stoichiometry problem, a limiting reactant problem, to be specific. These two are going to react, but one of them is going to run out first, right? There's less of this. Once all of this reacts, nothing else can happen. So we're going to say that all of this reacts, that's going to decrease by 0.025 and get to approximately 0. If this decreases, this also decreases by the same amount. So this goes down by negative 0.025. We end up with 0.075 moles. On the other side, for every mole of A minus that's reacted, for every mole of H plus that's reacted, I'm going to gain 1 mole of this. So the change here, same number, different sign. And we get the moles. Okay? This is not how we looked at stoichiometry in Chem 1A, but it's the same idea. And I think it's actually easier. We're not asking you to calculate the theoretical yield, right? We don't need to know that. And it's already in moles. We're not giving you some grams and some milliliters and molarities and making you do all that stuff, right? Here's the moles. The worst thing that'll happen is they'll give you a volume and a concentration. Well, multiply them, right? So you get the moles. You look at which one of these is smaller. That's the change. It goes down on this side, so this becomes 0. It goes up on that side, done. So that's the first part. Then the second part. So adding the strong acid is equivalent to changing the initial concentrations. And that's what we just did in the MICMA table. Now, I know, I got to find something better, but we need to calculate the new pH. We can do a full equilibrium problem with an ice table, or we can use the Henderson-Hasselbalch equation. It says here calculations can be done in moles because the volumes are the same and thus cancel out. That is true, but of this particular kind of question, but it's not always true, and so I would not encourage you to do that. Sometimes a shortcut really backfires because you get the wrong answer. And if you just did it the same long way every time, you get the right answer. So you can use that if you want to at your own peril. So here, this is the molarity of HA. And how do we get from moles to molarity? We divide by the volume in liters, right? And so this was 0.0125 moles in the previous table. The volume's 1 liter, so it's 0.125 molar. This is 0, and this is 0.075. These numbers came from the previous table. And then we'll put in our X changes and put those together. And we need the equilibrium constant, and then we could solve for X and find the pH. Yes?
So the MICMA table is basically finding the initial for the ice table.
Right. The MICMA table finds the initial amounts, the initial concentrations for the ice table, or for the Henderson-Hasselbalch equation. Yeah. Questions? What if we add base? If we add strong base to a buffer, the effect is the opposite. So we're going to make a MICMA table again. What are we adding? We're adding base. So start this chemical equation with what's being added, hydroxide. And which part of the buffer is it going to react with? It's going to react with the acid, okay? And so then what does that form, right? So that's your equation, that's the top, the header of your table. So if we added 0.025 moles of hydroxide, and we had the same initial amounts of the buffer, this is the limiting reactant, so all of that's going to react to leave 0, and this is the same number that's used on the other things. It's subtracted here and added there. Okay? And then you're going to use these numbers in your ice table or your equation. Any questions? Clear as mud. So if you add strong acid to the buffer, it's going to react with the base in the buffer, a stoichiometric amount, and that will create acid. So it will decrease in pH, right? What do you expect if you add acid to something? pH is going to go down. The pH is still going to go down. It's just not going to go down as much. If we add a strong base to the buffer, that's going to convert some of the acid in the buffer to the base. That's going to cause the pH to increase. If you had water and you stick sodium hydroxide in it, do you expect the pH to go up or down? It's going to go up. I put base in it. Same direction, it's just the change is smaller. So here we have in the middle equal amounts of the weak acid and its conjugate base. And here they are depicted as little circles. So if I add acid to this, so their hydrogen is kind of grayish, right? So if I add a hydrogen to this, it's going to stick on one of these guys, right? That's what it's going to do. So now I'm going to have one less of these and one more of those. So over here, I've got 5 and 3 when I started with 4 and 4. Adding hydroxide. Well, hydroxide is going to take, well, let's get rid of this. If I add hydroxide, that's going to take a hydrogen off. So now I'm going to have one more of these and one less of those. Everybody okay with that? I remember first learning about buffers, and it was kind of confusing. And then when you see how they work, you're like, that's genius. That's so amazing. And it is amazing. And your body does this all over the place. It's part of what keeps you alive. Okay, so we're supposed to closely examine this figure. Which of these, A, B, or C, best represents how much hydroxide is added to the buffer to get this result? Are we adding 1, 2, or 3 hydroxides? 1. Yeah. Oh, I'm writing with white. Can you tell? Adding one of these will steal one of these hydrogens, giving us 3 of those. This one that's lost the hydrogen becomes one of those when we've got more of those. Okay? Any questions? So no matter what you throw at it, an acid or a base, it can make the change less. Okay, a 1 liter buffer solution contains 0.1 moles acetic acid and 0.1 moles sodium acetate. Because the initial concentrations are equal, the pH is equal to the pKa, which is 4.74. Calculate the new pH after adding 0.015 moles of sodium hydroxide. Is it going to go up or down? It's going to go up because we're adding base, right? So the first thing we have to do is make the funny name table. The one I had before was a BA table. B, A, and A. BA. So I don't know. MICMA is a little less embarrassing to say. Yeah. Anyway, so what are we adding? Hydroxide. So that's what we start our chemical equation for that table with. What does the hydroxide react with? Reacts with the acid, right? Let's just be different and actually write the whole stupid thing out. We're assuming this reacts completely. And then that's going to make H2O and C2H3O2 minus. So, moles initial, change, moles after. How many moles of hydroxide are we adding? It says 0.015. Here, they told us the volume. They also told us how many moles were in there, so we don't have to do any conversions. There's 0.1 mole of the acid and 0.1 mole of the conjugate base. And we don't care about the water. So one of these things is smaller than the other, right? The 0.015 is smaller. That's going to get all used up. So subtract 0.015, subtract 0.015, and on the other side of the arrow, add 0.015. And then add those two rows, we get 0, and I think this was 0.085, and this is 0.115. Any questions? So these are moles. To do an ice table or a Henderson-Hasselbalch equation, we need molarity. So the HC2, H3O2, I'm writing this out. You don't have to write it out, but just to make sure that we see what's going on here. It's that many moles divided by the volume of the solution, which was 1 liter. And the acetate now is 0.115 moles in 1 liter, which is 0.115 molar. There will be times, many times, where it's not a liter. And Because here, if we're adding solid sodium hydroxide, we can say, well, that's not really going to change the volume that much. But if we were adding a solution of sodium hydroxide, it would change the volume, and we'd have to use the new final volume to calculate the molarities. So pH equals pKa plus log of base over acid. So pH equals, the pKa is 4.74 plus the log of the base, 0.115, divided by the acid. .8713. .87. Any questions? Yeah. If the problem gives you the pKa, do we assume that we can use Henderson-Hasselbalch? That would probably be safe. There are some things in the homework questions where they might try to trick you with something, but I'm attempting not to trick people on an exam unless I warn them ahead of time. I'm going to try to trick you with this, like the kilojoules joules thing, right? But then am I tricking you if I warn you ahead of time? Not really. Any other questions? Okay, so that was a buffer that was a weak acid and its conjugate base. You can also have a buffer that's a weak base and its conjugate acid. So NH3 is a weak base. This is the conjugate acid. Because NH3 plus water, the base takes a hydrogen ion and produces hydroxide ion. This is the NH4 in ammonium chloride. The chloride is the counter ion. We're not going to pay any attention to it. So if we're going to do a calculation with a buffer that's a weak base, the calculations are similar, but we're going to need the Ka, and they're going to give us the Kb, or the pKb. So this is a useful relationship. The pKa plus the pKb equals 14, just like pH plus pOH equals 14. So here's weak base, ammonia, put that in there. We're putting ammonium chloride in there. And so now we've got a weak base and its conjugate acid. There's these counter ions floating around, and there's a little bit of hydronium ion from the water. Any questions? Calculate the pH of 1 liter of a buffer solution that's 0.5 molar in NH3 and 0.2 molar in NH4Cl when 0.01 moles of solid sodium hydroxide is added. Never mind. I just thought of something I should have pointed out, but it's gone now, so it's fine, whatever. So we have to do stoichiometry first. So look at what's being added. Sodium hydroxide. Do we care about the sodium? No. Highlighters don't work for writing either. So we've got hydroxide. And what's that going to react with? NH3 or NH4 plus? NH4 plus. The one that has more hydrogens on it. And we're going to assume complete reaction. So this is going to steal a hydrogen ion and become water. And that's going to leave us with NH3. So our initial moles, they're telling us the number of moles there, 0.010 moles. And ammonium, so here they're giving us concentrations, molarities, but again, they made it simple because this is 1 liter. They're definitely not going to do that all the time. And here they might give you the mass of sodium hydroxide instead of the moles. So this one's 0.2 moles. We don't care about the water. And NH3, 0.50 moles. We'll look at the change and the moles after. We're looking for which one is there less of? The first one, the OH minus. So that number is going to be the change. We're going to subtract it on this side so that that's 0. And we're going to add it on the other side. I don't know what I'm doing. So we're saying, okay, the buffer is going to completely neutralize what we threw in there. Is that going to cause a little bit of shift in the equilibrium? Yes, it is. That's why we have to do an equilibrium problem or the Henderson-Hasselbalch equation. So these are molarities. I'm sorry, these are moles. We want molarities. So we're going to divide by the volume, right? Divide by 1 liter. So this is 0.51 moles per liter. And this is 0.019 moles per liter. pH equals pKa plus log of the base concentration divided by the acid concentration. So this is the base concentration. And this is the acid concentration. They gave us pKb. Anybody thinking, well, why don't we just have a different form of this equation that uses pKb? You could make one. But how hard is it to change pKb into pKa? Not hard. 14 minus 4.75. So don't try to mess with it. Just leave it alone. Leave the equation alone. The pKa here is equal to 14 minus the pKb that was given. 9.25. something wrong. (14 minus 4.75). It's 9.25. That's the base, that's the acid. What are you guys getting? I'm getting 10.68.
Oh, I think it's your NH4 plus. There shouldn't be a 0 in front of the 9, or the 1 9.
Thank you. That's it. Yep. I've got an extra 0 here. So get rid of that guy, get rid of this guy, get rid of this guy, and that's going to change this to the 9 that it is supposed to be. Thank you for catching it. There we go. Like, what the heck? And then you can ask yourself, well, does it make sense that the pH went up? The added hydroxide. Did it go up very much? Not really, right? 9.25 to 9.68. It went up, but not as much as it would have if you just added that by itself. Any questions?